Hi class, here is another math review video for those of you who need a little bit of a refresher, or those of you who feel like you need to remind yourselves of the sorts of things that you need to be able to do in this class. The last time we talked about scientific notation. This time I want to talk about graphs and reading graphs. And certainly right now, with the world in the state that it's in, we're all getting a lot of practice reading graphs, but I want to just review the fundamentals so that we can use them both to gather information but also to represent information to each other as we go through this course. So with graphs, there are as many choices about how you draw graphs as there are different graphs that you've seen. There are different types of graphs. There are some graphs that are good for some kinds of data and other graphs that are better for other kinds of data. We can't possibly talk about all the different kinds of graphs that we might encounter. So I'm going to talk about the fundamental graphs, graphs that are either representing a function or graphs that are representing data that we've collected. Okay, and in those kinds of graphs, we basically define the graphs that we talk about based on the way we draw their axes. So there are two different kinds of axes, and we combine them in basically three different ways. So what are the two kinds of axes? So the first kind of axis is the one that you're used to. It's what we call a linear axis. Okay, now the up and down, the vertical or the y-axis can be linear, or the x-axis. For our purposes here, while I'm sketching things out, I'll draw everything horizontal because it's easier. So a linear axis is an axis where all the values along the axis are spaced out evenly and represent the same amount of value change as you go from one mark to the other. So if I put a couple of, or a series of individual marks down the page here, all spaced evenly, and this may be anything we want to measure. So let's suppose it is the mass of a planet, and the units in this case are units of the mass of the planet Jupiter. So whatever value you get along this axis, you multiply it by the mass of Jupiter, and that's the mass of the planet. Okay, and so along the axis then, I would simply label 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay, so a planet here is 2 times the mass of Jupiter, a planet here is 7 times the mass of Jupiter. Now the other kind of axis that you will encounter is called a logarithmic axis. Logarithmic, I probably spelled that wrong, and usually we just call those log axes. Okay, and here, for those of you who are math nerds, when we say log, this usually means log base 10. Okay, so logarithmic axes are a little bit different. So they're still straight. Okay, so I'll draw a straight horizontal axis. Okay, and let's label this age in years. So maybe this is the age of an asteroid, or the age of a planet, or the age of a solar system, who knows what. Now, logarithmic axes are a little bit different. So in this case, let's start by imagining a couple of evenly spaced points. So here's my first tick mark, here's my next tick mark, and here's my third tick mark. So on a logarithmic axis, as you go along the axis, you count, as you would normally, until you get to a power of 10. 1, 10 to the 0, 10, 10 to the 1, 100, 10 to the 2, and so on. Okay, so if I was counting along this axis, the first one I get to 1, 0.1, 0.2, 0.3, all the way up to 1. And then I start counting not by the unit I was counting on the left side. So on this side, I was counting in increments of 0.1. I now start counting in increments that are 10 times larger. So over here, I'm going to count in increments that are 1 unit. 1, 2, 3, 4, 5, 6, 7, 8, 9, until I get to 10. And then over here, I'm going to count in increments that are 10 times larger than that. So over here, I'm going to count in increments of 10. 20, 30, 40, 50, 60, 70, 80, 90, 100. and so on as we go along. Okay, so each of these gaps here where you're counting in a different size increment is usually what we call a decade. Okay, and so what you see here is a way to represent data that has wildly varying values across all the data that you have. We will certainly see the case, mass or age is a good example, where we are talking about things that are maybe 10 years old or 100 years old or 1,000 years old, and we're still going to need to represent in the same data set and on the same graph things that have ages of 1 billion years or 10 billion years, and logarithmic axes let us do that. Now what's weird about logarithmic axes is here in these increment parts is that the spacings are not equal. And I haven't drawn them here because I can't draw them accurately, but let me just give you a sense for how they go. So let me zoom in here just a little bit so you can see. Okay. So in this case, what I'm going to do is I'm going to divide this increment up into, and it looks like it's not focused there. So here, let me back off a little bit. There we go. Okay, so in this case, the increments that are, say, 2, 3, 4, 5, 6, 7, 8, 9, they get closer and closer together as you go across the interval. Okay, so when you're reading off a graph and I draw my line up to my data point, I have to count over how many am I. If I'm over this one, the value here is actually 3. If I'm over this one, 3, 4, 5, this one's actually 6. Similarly, over here in this decade, when I'm going up over it, there is 20, 30, 40, 50, 60, 70, 80, 90. If I'm over this one, that's 10, 20, 30. In this one, I'd be over 30. Okay, so using logarithmic axes this way is a little bit taxing to read and draw, and so especially when you draw logarithmic axes, we tend to have them drawn automatically by computer. Quite by chance, what you'll see, this scratch paper that I'm using is actually called logarithmic paper. So back in the olden days when we didn't all have laptops, we used to use log paper directly. So this is called semi-log paper because it has logarithms along one axis and normal spacings along the other axes. Okay, but we're going to do all of that on computers with spreadsheets and stuff if we have to do that this quarter. Okay, so these are the two different kinds of axes, and so you can make a choice when you make a graph of what the horizontal, the x-axis is, and what the y-axis is. Okay, and so there's basically three choices. Okay, so the three common choices are where you have a linear vertical axis and a linear horizontal axis. The second choice is when you have a linear horizontal axis and a logarithmic vertical axis. And the third choice is where you have a log axis on both plots. On both axes, okay? And so these go by different names. This one's usually called a linear plot and sometimes an ordinary plot. I don't think there's an official name called ordinary, but when most of us say the word ordinary, that's what we mean. This one is usually called semi-log, and I'll show you examples of all of these here in a minute. Okay, so a semi-log plot means the vertical axis is logarithmic and the horizontal axis is linear. And then this one is usually called a log-log plot. Sometimes you'll hear people just call it a log plot, but usually when people say log plot, they mean log-log. Okay? Okay, so let's take some example graphs and show you what those look like. So I've pre-prepared some of these. In the scan notes, I won't go through these here on the video, but in the scan notes you'll see some examples with real data. So these are linear, semi-log, and logarithmic plots of exoplanet data, and we'll talk about exoplanets in a couple of weeks. But let me show you all three types of plots using data from our solar system. So this is a plot of what's called Kepler's third law, or the harmonic law, which basically tells us that the period of a planet's orbit is related to the size of the orbit. Basically, as you get farther away from the sun, then the time it takes you to go around the sun goes up. Okay, so this is a ordinary or linear plot. So the horizontal axis is plotted linearly. So semi-major axis is the size of the orbit. If it's a circular orbit, semi-major axis is the radius of the orbit. Okay, and AU is astronomical unit. That's the distance between the Earth and the Sun. So what we've done here is we've described the orbits of all of the planets in terms of multiples of the size of the Earth's orbit. Okay, so 10 AUs, 20 AUs, 30 AUs, 40 AUs is the multiple of the size of the Earth's orbit. So the red line is the theoretical derivation of Kepler's third law. We'll talk about that later in the quarter. And then the blue dots are the actual values of the planet's orbits. And what you can see is they fall exactly along Kepler's law, which you would expect because the way Kepler figured out Kepler's law was by looking at the orbits of the planets in the solar system. Okay, so on the vertical axis, this is the linear axis. This is the orbital period in years. And so you see we're going up in increments of 10. So this is 10, 20, 30, 40, 50. And between the big horizontal lines, they're increments of 50 equally spaced all the way up. Now, I chose to represent this data in a linear plot, but I could have just as easily chosen to represent it with some other kind of plot. So here's the exact same data in a semi-log plot. Okay, so in this case, this is still Kepler's third law. The red line is still the function. The blue dots are still the actual values from the planet. I'm plotting in the linear axis in the horizontal, the semi-major axis in astronomical units, so it looks exactly like the graph on the last one. But in this case, I've chosen to represent the vertical axis differently, in this case logarithmically. Okay, and so you can see in the lower part of the graph, I go to 1. So as I go up these tick marks, I'm changing the value by 1 astronomical unit. And then in the next part of the graph, I'm incrementing by down here in tenths of an AU, I'm now incrementing in units of 1 AU, and then above 10, I'm increasing in increments of 10. Sorry, these are years, not astronomical units. Wow. Okay, I'm not going to record that whole video, okay, but this is still logarithmic. Okay, now I could have also chosen to plot it as a log-log plot. Okay, and here on the log-log plot, you see the graph looks very, very different. It's actually a perfectly straight line. So here I have the logarithmic size of the orbit in astronomical units, in tenths of an astronomical unit, in single units of an astronomical unit, and then in tens of astronomical units. And here I have the logarithm of the orbital period. So here it is fractions of a year, here it's in years, here it's in 10 years, here it's in centuries. Okay, now this shows you why you often choose to use different forms of the graph for different types of data. On log-log plots, if the line is straight, that tells you something about the nature of the function or the nature of the data. In this case, it's what we call a power law. Okay, so a power law is a straight line on a log-log plot, and what it means is whatever you're plotting on the y-axis, in this case the orbital period, is related to whatever's on the x-axis by a power. Okay, so on the x-axis we label semi-major axis A, and in this case the power is 3/2. So as you increase the size of the orbit, then the orbital period increases by that factor to the 3/2 power. Okay, so that's a power law. In this case, you may remember when we looked at the semi-log case, the line was curved. Okay, but there are cases where the data on a semi-log plot is a straight line, and on a semi-log plot, you get straight lines for exponential functions. Okay, and so most of us have been looking at exponential graphs related to the current global pandemic. And so this is one of the ways that we know the data is exponential, is when we plot the data related to the global pandemic on a semi-log plot, where there's some value on the vertical axis that is plotted logarithmically, and then whatever value is plotted on the horizontal axis, typically time, is plotted linearly. Then that data comes out as a straight line, and that's how we know it's exponential. Okay, so one of the things that happens often when we work with data is we put it into a graphing program, a spreadsheet, and we make a plot, and then we just try all three versions of the plot to see if it shows some special structure. And if it does, then we choose that value of the plot to help illustrate that the data has this special property. If the data doesn't show that it has any special property, and this was certainly the case of the exoplanet data that I showed you originally, okay, so this is just the scattered data of all the exoplanet data. Sometimes there's really no pattern to the data, and that's fine too. In those cases, you make the choices of which graph you're going to use in order to spread your data out so that you can actually see all of it at once and it doesn't all bunch up. So here on this plot, you can see lots of the data is bunching up along that axis. So that's another reason to choose different values for the plots. Okay, so I think that's all I want to tell you about graphs. I've talked about all of this in the notes online, so you can certainly go take a look at them. And we'll have one more math lesson after this. We're going to talk about units and how do we convert units so we can talk about big numbers in the universe. Okay, good luck everybody.